Continuing on with Chapter 5. So, shaping stream valleys, there is a base level that a lowest stream can erode to. There's two general types. There's the ultimate base level, which is, of course, the ocean. So, we say that occurs at sea level with zero altitude. And there could also be temporary or local base levels. And you can transition between different base levels essentially by different methods. One common method would be a waterfall. So you can see in picture B here, you have one local base level, which is at whatever this altitude is, and then you have your waterfall, and then eventually you have a different base level after that waterfall. And these can change depending on what's going on in that geographic region. So valleys can be shaped by different processes, and by some of the processes we talked about in Chapter 4. So you could have weathering, overland flow, and that other topic called mass wasting, which is essentially just gravity pulling rocks down from different mountainsides. So there are some characteristics of narrow valleys you should know. Narrow valleys are V-shaped, downcutting towards base level. You have something called incised meanders, and you have features that often include, as I mentioned before, rapids and waterfalls. Now, wide valleys are more interesting. So the stream is near the base level at wide valleys. We have downward erosion is less dominant, and we have stream energy directed side to side. So here's an example of a V-shaped valley of Yellowstone River. So you can see that the river is not very wide here. So you have rapids forming because all of the river deposits are kind of closer together. So you have water bouncing off of and moving past different materials in the river. So you have rapids occurring more often in these V-shaped valleys. This is a slide that shows you how you could have a floodplain developing. That's another characteristic of a wide valley. So how this works is that when you have erosion in a river, what I want you to get out of this is that near the edge of the river is where you have erosion. So you can see here in this picture, this curve in the river, we call these meanders. Let's just say it started here. As time goes by, you erode more and more of this edge of the river away, eventually until you form a floodplain. So these meanders, since the erosion occurs again at the edge, it keeps eroding and eroding away even more of the geography in the region, such that the river actually just becomes wider. So floodplain is that characteristic of a wide valley. So you can include those in wide valleys. You could have meanders, cutoffs, and oxbow lakes. So what's an oxbow lake? They're pretty interesting. This is not an oxbow lake. This is just a very large meander. But what will eventually happen is at this location here where I'm moving the mouse, you're going to have erosion on this side of the river near the edge of the river, and then the same thing over here. You're eventually going to erode this piece of rock away so much that you're going to end up just having a body of water here, and the river is going to continue to meander and cut off this piece of river, which will then become an oxbow lake. All right, so just some information about floods. They're obviously the most common geological hazard, and they can be caused by weather. If you have a very large amount of rainstorms happening in succession, you can have natural flooding. But then also you can have floods occurring because of human interference with that stream system. So there are some engineering efforts to try to control floods. You can make an artificial levee, which is just a buildup of the side of a river to attempt to contain a river if it increases in depth as you have more and more water coming from the head of the river. You could have flood control dams, and then also something called channelization. So there is also non-structural approaches through sound floodplain management as well to control floods. So here's an example of what a river would look like when you have a very large flood due to increased weather in that region. So this is from a picture on the top is from 1991. So this is the Mississippi River, Missouri River, where the Missouri River goes into the Mississippi River. So you can see in 1991, this was the original size and width of the river. And then in the next 2 years, we had an increased amount of weather in that region, so a lot more moisture precipitated from the atmosphere. And you can see that the width of the river increases dramatically in that region when you have a flood. Okay, moving on to groundwater. So this is the largest freshwater reservoir for humans. So there are geographical roles for groundwater. It could act as an erosional agent, and this could dissolve rock around that area to create things like sinkholes and caverns. It's also an equalizer of stream flow. So the distribution of groundwater, there's something called a belt of soil moisture, and then a zone of aeration, which is just the unsaturated zone underground where there's no water, and there's pore spaces in the material that are filled mainly with air. All right, so the zone of saturation, this is where all pore spaces in the ground are filled with water. So water within these pores is considered groundwater if it's in the zone of saturation. So the water table is the upper limit of this zone of saturation. So there's going to be some words in this picture that are going to be defined on subsequent slides. So the distribution of groundwater, something called the porosity, is the percentage of pore spaces that you have, and this determines the maximum amount of storage of groundwater. And then you have permeability. So this is the ability to transmit water through connected pore spaces. So there's two types of areas underground for permeability. You have an aquitard, which is an impermeable layer of material. So this is where water cannot pass through. There's no way there's not enough pores for water to pass through. And then there's an aquifer, and this is a permeable layer of water. So features associated with groundwater, you could have springs. So you could have hot springs. So this is water that's generally 10 to 15 degrees Fahrenheit warmer than the mean air temperature in the locality. So it's going to feel a lot warmer than the surrounding air, but it's not super hot like it's going to burn you for the most part. And this is heated by the cooling of igneous rocks. So you're going to have igneous rocks underground. Again, there's going to be a source of magma nearby. It's going to be warm, and then when it comes to the surface, the water in the ground, so the groundwater will then heat up because it's going to cool the igneous rock around it. And then you have geysers, which is just intermittent hot springs, and it's water that's turned to steam, so it's hot enough to at least boil the water. And this is just an example of a geyser at Yellowstone National Park. So there's certain features associated with groundwater. We have a well, so this is just something that pumps water up from the water table. So pumping can cause a drawdown or a lowering of the water table. Pumping can also form something called a cone of depression in the water table, and there'll be a picture associated with that in a second. And the second type of well is called an artesian well, and this is water in a well that rises naturally due to the location of the water table. All right, so here's an example of the location of the water table. So if you want this area to have groundwater or some type of drinking water, you would put a well and then pump the water up from the water table. Now, if that pumping was so heavy, what is possible is a local depression in the water table, which is called a cone of depression. So eventually, if you had, let's say, multiple wells in this region, if you had one pumping so hard, it could actually dry up other wells nearby by locally lowering the water table. Here's an example of an artesian well, which is kind of interesting. So if you have a water table that rises high enough such that a well at a lower elevation, right? You can have, since you have higher pressure here and the water is going to flow this way, the high pressure here at number 1 will cause the lower elevation well to actually push up water just due to that pressure difference. So that's a naturally occurring well, would be an artesian well that flows on its own without having any type of mechanical pumping system. So there are environmental problems associated with groundwater. You can have localized heavy pumping of water create an actual altitude change in an elevation. So this is a very extreme case. This is the San Joaquin Valley in California. So it's showing you the current level. Well, this was a picture taken in 1977 compared to what the elevation was in that region in 1925. So you can see there was a 9 meter or 30 feet drop in elevation just due to water pumping out of that area in that time period. There's also a lot of naturally occurring things that groundwater does underground. Groundwater is often not basic or doesn't have a pH of 7. It would be actually lower than 7, so that would make it acidic. So that can combine with carbon dioxide to create a weak carbonic acid. So what this could do is it can form caverns by dissolving rock underneath the Earth's surface. And this is typically formed in the zone of saturation because you have to have water for this to happen. So sometimes you can have features found within these caverns. You can have dripstone, you can have calcite depositing as dripping water evaporates, and you can have something called stalactites, which are large rock formations hanging from the ceiling of the cavern, or stalagmites, and these grow upward from the floor of the cavern. You'll also have something called karst topography found in regions where there's a lot of groundwater. So these are just formed by dissolving rock at or near the Earth's surface. So some common features in these areas would be sinkholes, which are just surface depressions. So sinkholes form by you basically just dissolving the bedrock, and then you have a cavern that's formed, but then that cavern collapses to basically form a large depression in the ground. Um, and these areas often lack good surface drainage. So this is just a picture of a karst landscape where you have multiple sinkholes in an area formed by an increasing river valley. And the water table is low enough that it lowers in the region such that you have all these caverns form and they eventually just depress and form all of these localized sinkholes in the area.